Thank you everyone for coming. Our talk today is overcoming outdoor connectivity issues. Hope that's the one you meant to come for. Please stay if it's not. My name is Amol Parikh. I'm the VP of Marketing at Doodle Labs. I'm going to tell you a little bit about what we do and actually put this in the context of how we design solutions for UGVs and specifically in the outdoor space. So at Doodle Labs, we've been around since like 1999. We've been involved in outdoor long-range connectivity since that time. We had a focus on just long-range Wi-Fi for a long time until we shifted that focus over to robotics and really building out robotics networks with drones, UGVs, AMRs, all that kind of part of our portfolio. Specifically today, the topic that we're talking about is designing a network for outdoor connectivity and some of those challenges that are faced for that, and why we see our solution set with our mesh radios as an upgrade or a better option when you can't rely on existing networks like simple Wi-Fi or LTE. So the challenge is outdoor networking is challenging. And when Wi-Fi and LTE don't cut it, I'm going to get into those details, but it's just some of the high level are you need to actually transmit too much data that a standard Wi-Fi network is going to be able to support once you start to scale up to more nodes, more robots on it. That's usually like the warehouse type of use case. Or if you're going to be deploying in a place like a new mine site or something that doesn't have built out infrastructure that already supports it with LTE coverage. So you're going beyond available coverage. Those are just some of those challenges. And so having that ability to bring your network with you is what we're really designed around. So the way that we refer to it is resilient private wireless mesh networks. That's what we're in service of. We have several form factors here that I can show you and I'll hold up later. But they're all just in terms of what are you designing around. Is it an air robot, ground robot, connected teams, a handheld situation, just in service of using your phone in those environments. That's what we've designed around, and that they can all actually work together. Our big idea actually incorporates all of those different types of robotics together. So why is outdoor networking challenging? The main thing is that when you're talking about mobile robotics and in outdoor environments, you have to take into account that you have moving nodes that are changing pitch, orientation, fade with whatever you're trying to connect to. And then when you put it into an outdoor environment, you have to contest with what type of environment is it? Does it have a lot of foliage? Is it a rural environment that has a lot of Wi-Fi noise? We do some work, we're dual use, we do some work with defense when you actually experience like jamming as an intentional interference on the link. Those are things that you have to compensate for based on what you're deploying into. So Wi-Fi networks are great for simple devices like laptops, phones, and generally scale up well indoors. But standard Wi-Fi networks can't support the high bandwidth, long range requirements of outdoor robotics. And it can suffer from that congestion and interference. And LTE works well for developed urban areas, but often isn't available in remote locations. And then another differentiator is just the operating cost. With LTE, you have a cost per node, a subscription cost, whereas if you build out an infrastructure based on mesh networking, you're just really building out, you're purchasing the hardware, and that's your only cost. You don't have an operating cost after that. What do we experience when our customers come to us saying that they tried a Wi-Fi network, but they needed to upgrade? And it's largely based on they have started to grow their network, like it's a warehouse that we have like 100 mesh node one of our customers is doing with AMRs. They started to crunch that network once they started to get over like a handful of robots. And that's also because that same network is being shared by laptops and tablets and all these other workers that are on it. So having a separate private network just for those advanced robotics is better. And so when you put that into outdoor spaces, you're just designing around what is the most robust and resilient thing that I can. You've invested a lot of money in buying these advanced robots. What can I support them with to make sure that they're functional, useful, reliable, so that my end user is going to feel confident that I can actually deploy it and it's not a waste. Something that we actually hear a lot is like, say, Caterpillar. We were talking with them, and they are making hundreds of thousands of dollars autonomous vehicles. They put it out at a mine site, and the first thing they hear is, hey, this thing isn't working. It's not that the thing isn't working, the network isn't able to support it. And as you know, with drones and on the ground, like, there's a safety protocol is if you lose link, the machine stops. And it just to make sure that it doesn't, hit anybody or something like that. That's where we come in with like a more advanced networking solution. Then at least that doesn't go down. Your end user can have more confidence that if they deploy this, they're actually going to get the use out of that robot that they were going for. On the LTE side, coverage is not always available. Yeah, we know that, just off-grid environments, things like that. Another thing that we actually experience, like on the some of the use cases of this is like disaster response, things like that. Infrastructure is expensive to build out to a place, but it can also be damaged. And so when you're not reliant on having to bring a network into a space through other infrastructure, then you are just a little bit more independent and able to actually even pick up and move based on wherever you have to move your whole robot system, the things that are around it, whatever you're designing around. And the last point is also kind of in service of that reliable link and being able to use your robot, you need low latency, especially if you're in terms of remote operation. You need that latency to be as low as possible so that you know that you have real-time connection to that system. And so that's something that we have on ours. There's an additional component to it, which is called the URLC, Ultra Reliable Low Latency Channel. It's just in terms of providing the lowest latency, it's less than 10 milliseconds connection to your robot. So that way you can ensure that you have like real-time control. So what I thought I would go through is like some of the challenges that you face when you're designing an outdoor network, or some of the considerations that you really have to plan around. And then what you'll see pictured is all just various customer use cases of ours, and with the logo below it. We did our best to marry it with each of these considerations I'm going through, but they're also just in reference to different UGV customers that we service. But in terms of bandwidth and latency, that's something that you have to think about. What is the data traffic that you need to transmit? And so therefore, what amounts of bandwidth do you need? Sometimes it is just position location, which is really, really low bandwidth. But sometimes it's HD video, 4K video. We can support all of that. Where we really find that it's worth it to upgrade to something like us is when you are in the high bandwidth category. If you only need low bandwidth, there actually are a lot of other solutions out there. And so streaming HD video is roughly with some encoding like 2 to 3 megabits per second. So we start at 80 megabits per second, and you have a degradation as you go over distance, and so you can go quite far with that. The remote operation of a robot is on the low latency that I already mentioned. So types of data transmission: HD video, LiDAR scanning, sensor data, command and control, telemetry. We really designed the link to be in service of actually you can send multiple of these together. Again, I mentioned that URLC, that's for the command and control and telemetry. But then you have the rest of your basically pipeline, your data link, available to high bandwidth data transmission, so HD video, things like that. The use case, actually, maybe I speak to it really quick. Here's a really neat one. It's this company, MVP Robotics. They make the whole system, but it's really just a dummy sitting on top of their UGV for target practice. They started with working with the NFL for tackling practice, but then they are also dual use, and so they work with various armed forces, but for target practice as well. In terms of interference, that's a big problem, can be a big problem when you're deploying and when you're building out a network. And so we have solutions that are on the commercial side, and then we have solutions that are on federal frequency bands, the licensed category. When you're in the licensed category, you generally have a lot cleaner spectrum to work with, but when you're on the unlicensed side, you contest with the fact that if you're operating in 2.4 gigahertz Wi-Fi, you can definitely deploy around the world. It's amazing, but you're also going to have to contend with every Wi-Fi device that's going to be causing noise in that spectrum. And so the way that we approach it, even though we start with Wi-Fi, we add a bunch of things to our waveform that actually, even though it's in 2.4 gigahertz, it's not going to actually interoperate with a Wi-Fi access point. and we have some ability to kind of drown out some of that noise. But we've actually went further with it and made all of our radios multi-band. So they cover both 900 megahertz and 2.4 gigahertz together, so you have two unlicensed frequency bands. And you have this sense technology, our interference avoidance, which actually allows you to move within a band to other channels when you start to experience interference, or move to the other band altogether. So it's just something to keep in mind, because especially with our customers that are in agriculture or focus on like drone delivery, places that are semi-urban or urban environments, you just are going to experience a lot of different RF noise. And so having just kind of like more tools in your toolkit allow you to like maintain a more reliable link. But that is something that you could face a lot in outdoor applications. Especially as we talk about ground robotics today, high-speed transmission, high-speed robots themselves, but low to the ground represent a challenge that you have to factor in. You know, again, we do a lot of work with drones. What they don't have to contend with is frontal zone obstruction, where the curvature of the Earth itself acts as an obstruction once you get to longer ranges. Different frequency bands have different physical properties. 900 megahertz actually suffers from that the most, and so it can be challenging to use on the ground. But if all of our radios are mesh, if you fly a drone in the middle, you're setting up a midpoint relay that is at a high point, and now you're overcoming those obstacles. And so those are things you have to design around as well, because once you actually send your stuff out, these are all different things that are going to factor into their reliability and like the productivity of your network and the ability to use your robot. Here is Robotics Plus. They're a customer of ours down in New Zealand. They have made this autonomous UGV that runs through these really large-scale industrial farms for spraying in pesticide, things like that. We've kind of touched on this, but topology, just the topology of the place you're actually deploying, it kind of is just the same thing as like RF noise. It's what is the constraints, the physical constraints of the environment that you're in that you have to factor around. So this one, you know, are you going to have really large trees that are going to get in the way of your link? Are you going to have to overcome like hills and things like that? Generally speaking, building out mesh networks, but you have this ability to overcome those obstacles, but you have to design around it. If you're trying to do just a point-to-point and you have two ends with a hill in the middle, you're going to have a hard time. But if you are able to send a midpoint of like either a drone or a ground thing, having a radio in the middle, you're able to beam over the hill. So those are just things that you plan for, knowing where you need to be. And those could be either fixed installations or like semi-fixed things of putting this up on a tripod, or it could just be another robot itself that you just kind of roll into the middle. Again, on our drone side, we have that where there was a situation where a drone had to overcome a large mountain or hill, and they were able to fly a second drone into the middle that maintained that connectivity, and they had line of sight to both ends of that network, and that's how you kind of overcome some of those challenges. Large networks just really represents like, how big are you trying to go? If it's just a point-to-point, it has its own set of challenges. If you're trying to actually scale this up to include a lot of different robots, you have to factor that in, or it might not just be robots, it could be people plus robots in the air and the ground. Whatever you're designing around and how large it needs to be, factor into other pieces of that as well. In terms of like, again, the warehouse situation, what they need there is really, really fast mesh, because they are moving at fast speeds and they need to go around turns, and they have these large metal racks that act as blind spots and cause obstructions just from these robots themselves. So being able to actually take what they use is our advanced mesh protocol, and instead of a break before make, which would be trying to actually send a signal path a certain way, doesn't make it to its destination, it retries a different route. That one is constantly seeking for the most optimal path, and it's a zero latency handover, and it's just constantly looking for what is the best way to send my data. That's something that they have to contend with, but sometimes you don't. So that's another factor to keep in mind. So all of those things that we kind of went through, that I did already speak to, like how we approach solutions in them, but our big idea is that resilient private wireless mesh network. The waveform that we have in our radios is called Mesh Rider. And so it's that high bandwidth capability, low latency. We're data agnostic, whether you're sending video to sensor data to just telemetry. We have that interference avoidance capability with Sense. We've designed these various use cases to be optimized for whatever you're building into. Smaller end, really low size and weight options for something that's in the air that has to carry components, so drones, versus like a handheld version like this, or popping off the battery. This is more of like a vehicle mounted or fixed access point. It's IP68 so that you can actually have it outdoors. It can handle rain and water. So various form factors for different use cases, all designed for long-range applications, and support scaling up on the mesh as you need, as well as with an advanced version. This is actually, an illustration, but represents the various types of robots that we have in our portfolio. We have a whole bunch of drone customers, as we had some focus on that for the last few years. We have UGV customers in agriculture, in construction. We have AMR customers in warehousing. If you guys know Boston Dynamics, this is literally just that because they use our transceivers and they're spot on. So when you are setting up a mesh network, kind of taking all those considerations into account, you're just looking at the way that we've put together a little white paper and a guide, and if you come by our booth, I think have given out most of them, but we have a couple of them left, and you're more than welcome to take them. But it's just kind of a walkthrough of, if you're designing this network, taking those considerations into account, what would we recommend is your approach to building out your network? And so first is thinking about, what do you need it to support? What are your system requirements? Do you have size and weight restrictions because you have a small robot, or you're sending it in the sky, or do you have none of those? And are you designing stuff that includes people? Think of those things first, and what type of data traffic, because that will kind of direct you towards which one of these to work with, or which multiple ones. You look at your area that you need to support the network with, at least a target area or an idea, especially if this is something that is a little bit more ad hoc, or ability to actually pick up and move it to other places. But looking at that type of environment, they have different rules about which frequency bands you can use in different areas of the world. That factors in. There's different RF noise in different types of environment, from urban to rural, those kinds of things. So you look at that. And there's a couple of recommendations, I guess maybe not here, but in our guide, that actually help you do that digitally or remotely, so you don't have to always go in person. At some point it will. Based on those factors, you can choose, and you'll work with us on this if you wanted to get in touch. And we help. We take a consultative approach to designing these networks, and so if there's any support we can have, we would ask questions that kind of glean the answers of those factors that I already mentioned, and we would help kind of make recommendations as to which one of our products we think is a fit. And then you plan the network layout. So actually kind of designing around your architecture and where you plan to actually deploy. This is how we approach all of our testing as well, or if we were to work with you and design what we think would be the best way of deploying the network. It starts with kind of a bit of a plan, and thinking through what of our products plus other components you need there. What I didn't mention here is that we're able to support any type of antenna that you want, but that can really change things quite a bit. We always recommend Omni. It helps when again, you're changing pitch, orientation, all those things on the robots. But we also know that when you have to go for super long distances, having a tracking antenna on one end can go much further. So while we normally get HD video over 20 kilometers, we have a customer that's doing 80 kilometers because of them optimizing around antennas and things like that. You configure the nodes, you configure the network. We have a graphical user interface that you use to configure our radios with some profiles based on the type of network that you're planning around to hopefully make that easier. We're always trying to make it easier. But you design around that, and you configure the network as you need, and then you go and test it. And what we find is that there's always usually a bench test where you get started with the radios just in the lab, but then it goes out into the field, usually right next to the wherever you're working with, next to the office, and then a pilot program that takes it into the field. And so testing it out there, starting to see if you actually are experiencing more interference on some things than you expected, things like that. So you can make some optimizations and changes as needed. Integrating with the controller, control station software. These are actually some examples of hardware, but where our radios are integrated into these controllers, or the one on the right is actually more of a modular thing that fits onto several different types of controllers. But there's different control software for drones than there is for ground robots, things like that, and building around whatever you're going to control your whole network. Finally, you get to deploy, and really see your UGVs in the field, and the hope is that actually you get there, you see them start to work, and that you actually can start scaling. Because I think we're focused on applications that usually have potential or expectation that is really going to start small but grow big. So that's kind of everything about us so far. This concludes actually the thing, but I'd love to take in any questions if you guys have any specific things you're curious about. Okay, well, thank you. Appreciate that. Yeah.
What's the power consumption?
Oh, good question. Actually, we're getting that a lot. So they're low size and weight and power consumption, but these ones have a different one than this. I would give you our data sheets, and I'd refer you to that for specifics. All of our radios on the unlicensed bands are 1 watt output power, though. So they're not too high in consumption, but they can get a little bit hot when you're blasting that HD video at long distances. But I'll be happy to take your info and I can send you our data sheets. Yeah. Yeah, absolutely. So the way that we approach our different frequencies, we actually start with a Wi-Fi chipset, and then we actually take a hybrid SDR, so hybrid software-defined radio approach, meaning there's hardware and physical components to it and software that allows us to frequency shift from 900 megahertz up to 6 gigahertz. And what that allows us to do is actually maintain the throughput of Wi-Fi, but actually take advantage of the physical characteristics of those different bands. And so one of our radios in the defense category actually goes from 1.6 gigahertz to 2.5 gigahertz. There's 6 adjacent frequency bands there. In that includes S-band, but then we also go down to 1.3 gigahertz at L-band. So we are able to produce radios at any of these kind of configurations. We have some that are commercially off the shelf. We have others that we could customize to. And it's really just based on our customer and their end user if they have that licensing approval. Thank you guys very much for your time.